Welcome back to the deep dive. Today, we're diving into a question that sounds kind of like science fiction.
Yeah.
Can we hear the rain on neutron stars?
Ooh.
You might be thinking, wait, rain on a star? But stick with us because it's even wilder than it sounds. We've got some fascinating research exploring how these incredibly dense stars might be generating gravitational waves. You know those ripples in space-time that Einstein predicted over a century ago?
That's right. And what's even more intriguing is that these waves are thought to be triggered by something called stochastic accretion. You can think of it like a cosmic shotgun blast where instead of pellets, it's random clumps of matter constantly bombarding the neutron star.
Okay, hold on a second. Let's back up a bit. For anyone who needs a refresher, neutron stars are what's left after massive stars explode as supernovas. We're talking about something with the mass of our sun squeezed into an object the size of a city. It's mind-bogglingly dense.
Exactly. And because they're so dense, they spin incredibly fast. Some of them rotate hundreds of times per second. Now, the research you shared focuses on a particular type of oscillation within these stars called R modes. Imagine you have a spinning top and it starts to wobble a little bit. Those wobbles are a bit like inertial modes, and R modes are a specific type that happens in rotating fluids.
Okay, I'm starting to get the picture. So we've got these super dense, rapidly spinning stars wobbling like a top, and they're being bombarded by this cosmic shotgun blast. What makes any of that create gravitational waves?
Well, remember, Einstein showed us that gravity isn't just a force, it's a warp in the fabric of space-time. When something massive moves or changes shape, it disturbs space-time, sending out ripples like waves on a pond.
That's right. So are you saying it's the wobbling R mode or the matter hitting the star that's creating these space-time ripples?
Both, actually. The RAR modes are disturbances within the star's fluid itself. And each time a clump of matter slams onto the surface, it triggers these raw mode oscillations. Think of it like each clump is a tiny meteor hitting the star and causing it to ring like a bell, sending out those gravitational waves.
I'm picturing a neutron star getting pummeled and ringing like some kind of crazy cosmic gong. So the bigger the clump of matter, the louder the gong and the stronger the gravitational waves.
That's a great way to think about it. The size and speed of the clump definitely matter, as does how long this bombardment keeps up. It's all factored into the equations used to predict the strength of these gravitational waves.
Okay, that's wild. But if all of this is happening randomly, how can we even predict what these gravitational waves will look like? Is it even possible to detect them?
That's where things get really interesting. The researchers in this paper have crunched the numbers, and it turns out that these impact-excited R modes probably generate waves that are incredibly faint, too quiet for our current gravitational wave observatories to pick up.
Oh, man. So even though we have these neutron stars ringing like crazy out there, we can't hear them.
Not yet, at least not these particular waves. Our current detectors, like LIGO, are amazing, don't get me wrong, but they're built to detect the really loud signals, like the final crash of two black holes merging. Think of it like trying to hear someone whisper in a rock concert.
So we need a way to turn down the volume on all the other cosmic noise to pick up these fainter signals. Is that even possible?
That's where the next generation of detectors comes in. There are already plans for observatories like the Einstein Telescope and Cosmic Explorer, which are designed to be much, much more sensitive. They'll be able to pick up those whispers we're talking about.
Okay, now that's exciting. So we just have to wait for the tech to catch up, and then we'll be able to eavesdrop on these neutron star concerts.
Exactly. But there's another layer of complexity here that we need to consider. Remember how we talked about those R modes wobbling like a spinning top? Well, under certain conditions, those wobbles can actually become unstable and grow out of control.
Okay, that sounds a bit worrisome. What causes that to happen?
It's a phenomenon called the Chandrasekhar-Friedman-Schutz instability, or CFS instability for short. It's a mouthful, I know. Think of it this way. You're gently tapping that spinning top to keep it wobbling, but suddenly someone comes along and whacks it really hard. That's kind of what the CFS instability can do to these waves inside the neutron star. Instead of just gently oscillating, the R mode gets amplified, releasing a huge burst of energy as gravitational waves.
Wow, so we could have regular ringing from these impacts and then these sudden bursts if the instability kicks in. How can we tell them apart?
That's a great question. The researchers actually suggest using something called the temporal autocorrelation function of the signal to differentiate between the two.
Right.
It's essentially a way to analyze the fingerprint of a gravitational wave signal and see if it matches what we'd expect from impact-excited R modes alone, or if there's evidence of that CFS instability amplifying things.
Ah, so we're looking for clues in the shape of the wave to tell us what's really going on inside the star. That's brilliant detective work. But Even if we can't hear these waves clearly yet, what can we learn from all of this? What makes this research so important?
That's a fantastic question. You see, neutron stars are like giant laboratories for physics we can't replicate here on Earth. The matter inside them is squeezed to densities we can't even imagine, and understanding how it behaves is a huge challenge.
So, by studying these waves, even the faint ones, we could learn something about the fundamental nature of matter itself.
Yes, absolutely. It's like having a window into the most extreme environments in the universe. By studying these impact-excited R modes, we can glean insights into things like the internal structure of neutron stars, how matter behaves under those insane pressures, and even how these stars evolve over time.
So, it's not just about hearing the rain on these stars, but about using those sounds to unlock the secrets of the universe's most exotic objects.
You got it. And while our current detectors might not be up to the task, the research gives us a roadmap for what to look for with those next-generation observatories. It's a glimpse into the future of gravitational wave astronomy and what we might be able to learn with more sensitive instruments.
This is blowing my mind. We've gone from rain on a star to unlocking the secrets of matter itself. But you mentioned that the properties of the neutron star also play a role in all of this. What kind of properties are we talking about?
Well, the most obvious one is the spin frequency of the star.
Yeah.
A faster spinning star will generate more powerful disturbances, leading to stronger gravitational waves. Imagine a figure skater spinning. The faster they go, the bigger the waves they create in the ice.
Well, one thing that really stands out to me is how this research challenges our assumptions about neutron stars. We tend to think of them as these leftover bits from a supernova, just cooling down quietly in space. But it turns out they're incredibly dynamic and active, constantly interacting with their surroundings in ways we're only beginning to understand.
That's a great point. This research really highlights that dynamic nature. It shows how seemingly chaotic events, like these random clumps of matter raining down, can actually generate these subtle ripples in space-time, offering us a whole new way to study them.
It's like we've been looking at these stars with blurry vision. And now gravitational waves are giving us a high-definition picture of what's really going on. It's fascinating. But if we're still waiting for the technology to catch up and detect these particular waves, what's the immediate value of this research? What can we do with it right now?
One of the most valuable aspects is that it gives us a blueprint for future observations. The researchers have identified specific characteristics of these impact-excited R modes and how they might show up in the data from more sensitive detectors. It's like they've handed us a treasure map highlighting the spots where we're most likely to strike gold once we have the right tools.
So it's not just theoretical, it's giving us concrete directions for what to look for as these new telescopes come online.
That's really cool. And thinking about those future telescopes, I remember you mentioned a special technique for analyzing the gravitational wave signals to tell if it's just the impact-excited R modes or if that CFS instability is also at play. Could you remind us how that works?
Of course, it involves looking at what's called the temporal autocorrelation function of the signal. It's a way to analyze the pattern of the wave over time. If those R-mode oscillations are being amplified by the CFS instability, it will leave a specific signature in the data, kind of like a fingerprint.
So it's like we're not just listening to the sound of the rain on the neutron star, we're analyzing the echoes and reverberations to figure out the shape of the room it's raining in, so to speak.
That's a fantastic analogy. By studying these subtle variations in the gravitational wave signal, we can tease out information about the conditions within the star itself. This is incredible. But before we wrap things up, I have to ask, out of all the amazing things we've discussed today, what's the one thing you really want our listeners to walk away with? What's the big picture takeaway from all of this?
For me, it's the sheer audacity of what we're trying to do here. We're talking about using ripples in the fabric of space-time, generated by these mind-bogglingly dense stars millions of light years away, to probe the fundamental nature of matter itself. It's a testament to human curiosity and our drive to explore the unknown.
It's like we're becoming cosmic archaeologists, using these faint whispers from the universe to piece together the story of how it all works.
Exactly. And this research is a perfect example of how that story is still being written. There's so much more we have yet to discover, and each new finding opens up a whole new world of questions and possibilities.
Well said. It's mind-blowing to think that something as seemingly simple as rain on a neutron star could hold the key to unlocking some of the universe's deepest secrets. And while we might not be able to hear those specific raindrops just yet, the future of gravitational wave astronomy is looking brighter than ever.
It certainly is. And I can't wait to see what other incredible discoveries await us as we continue to listen to the symphony of the cosmos.
A huge thank you to our expert for guiding us on this incredible deep dive into the world of neutron stars and gravitational waves. And to our listeners, thank you for joining us. We'll see you on our next deep dive into the fascinating corners of science and knowledge. Until then, keep looking up and stay curious.